My name is Max Coplan. I am a physics student and a student ambassador at Towson University. And today I'm going to be talking about beyond the black hole horizon with Mathematica, in which we use Mathematica to model the interiors of black holes, the only places in the universe that we will never be able to observe. So, black holes are a very hot topic right now in physics. Recent observations have proved beyond a doubt that the paradoxical warping of spacetime that Einstein claimed could never exist are in fact real. And in fact, the Virgo and LIGO telescopes have just a few weeks ago detected their fourth merger of these black holes, as you can see in this animation here. I mean, actually, just a few days ago, they had detected a fifth merger, except it wasn't with black holes, it was with another very fascinating kind of cosmic object, neutron stars. So actually, for this feat of these new insights into black holes and their mechanics, the 2017 Nobel Prize has just been awarded to Kip Thorne, Rainer Weiss, and Barry Barish. That's not Game of Thrones. All right. So actually, Kip Thorne is, I'm sure as many of you know, he's a big Mathematica user. And if you've seen his movie Interstellar, a lot of the prototypes for the black hole graphics and animations were actually first done in Mathematica. So let's look back at this for a second. So these measurements that LIGO and Virgo have done have revealed a new horizon of research and understanding of black holes. For example, the existence of previously undetected mass ranges for black holes. And as our technology continues to increase and our instruments get more powerful and accurate, our ability to see and detect black holes will become ever more accurate, and we'll be able to see black holes in ever higher detail. I mean, just seeing over the last couple of years, I mean, we can see these black holes, in tremendous detail, and it's only increasing. However, no matter how much we increase our technology, and regardless of whatever future advancements we may make, we'll never be able to see inside a black hole, regardless of how good our technology is. So, black hole, let me make this a bit bigger. 80% is a bit, let's try. So black hole interiors are the only places in nature that we can never observe by definition. And therefore, the only way to see into them is through mathematics. And this has already been done, but these existing visualizations are oversimplified and approximated to the point of actually being misleading. So for example, here is a common type of visualization of the black hole interior is just a basic black hole with mass and spin, both out charge, mapped out in Boyer-Lindquist coordinates. And this highlights certain features such as the singularity here and the event horizon in the ergosphere. But again, this, as well as other visualizations, are almost misleading because they all use coordinate-dependent quantities. So let's talk a bit about that. So the reason that this picture, right, the reason that it looks so simple and it's this constant curvature here, it's because of our choice of coordinate systems. But as many of you know, coordinate-dependent quantities can be misleading. So if you look at this map of Greenland versus the United States, it's pretty obvious that Greenland is larger than the US, and Alaska combined, I mean, easily, given this projection of the Earth. But if we look at the Earth from another perspective, so if we look at the Earth from another perspective, we can see that their sizes have almost reversed. I mean, here it's easily apparent that the United States is much larger than Greenland. And the reason for this is because these were mapped out in coordinate-dependent ways. So if we want to be sure of drawing true conclusions from things, we must express our results in these terms of invariants, which are quantities that don't change. Quantities whose values remain the same, regardless of any kind of transformation you use. So our objective here was we focus on the curvature of spacetime inside the black hole horizon. And mathematical physicists have proved that, that this curvature is characterized. So there's 17 different quantities of black hole curvature that do not depend on that don't depend on your coordinate system for the most general type of black holes. So what me and my team have done is that we use Mathematica's unique capabilities, because you really need a symbolic language to do things like this for a general case. And Mathematica is the only thing that really that's capable to calculate and plot all of these invariants for the first time. This is the first time that all 17 curvature invariants of black hole interiors have ever been mapped out. And the results differ dramatically from that basic, picture that we saw before. So before I get into the cool pictures and what it looks like, I can't show you what this stuff is without doing a little bit of math. So the most fundamental part of general relativity is the relationship that gravity is the shape of spacetime, and the shape of spacetime is gravity. And mathematically, these are described by the metric. And so in a sense, the metric, gravity, and the shape of spacetime, they're all very closely intertwined. And the metric, in a sense, is a generalization of Pythagoras' theorem, which states that the distance between, in 2D, the distance between 2 points squared is just would be x squared plus y squared. Well, in this case, it's, x, y, z, and time. Well, minus ct squared. But anyways, so for some examples of the metric, for flat spacetime, when there's no gravity, right? Since gravity is the shape of spacetime, if there's no gravity, there's no curvature. So that's why, so spacetime is flat when there's no gravity. And then a bit more of an advanced example of a metric, although still pretty simple, is the Schwarzschild metric, which describes the spacetime around a black hole that has a mass but no charge or spin associated with it. And the quantities that we're interested in are constructed by taking the metric and combining it in different ways with its first and second derivatives with respect to space and time. And as you can see here, these things get increasingly more complex. And as you take more derivatives with respect to space and time, the number of terms just goes up incredibly fast. So while we were trying to do this, we came into two main challenges. Our two main challenges was first trying to figure out how to translate the language of general relativity and Einstein notation into Mathematica syntax. Actually, while here at the conference, I've already learned much better ways of doing this. We almost had to come up with this from scratch, so that was, there are definitely more optimal ways to do it than in here. But our second challenge was once we translate this language and we try to compute the invariants, we get literally dozens of pages of output. And you can't do anything with it. It's impossible to understand. Mathematica's built-in simplify and trig reductions really doesn't do much. So these were our two main problems. So first, to translate the language of GR into Mathematica, we started looking at some resources, and a basic version of this we found in we found in a textbook, and we took that and we extended it, and we made it much more robust. So what we have here is we have the metric for a general black hole inside of it. So maybe we could look at this traditional view to make this make a bit more sense. Now, what we have to do is that we have to compute the inverse metric, the Christoffel symbols, the Riemann tensor, and the Ricci tensor and scalar. So with this code, we were able to do that. So if we just, let's undo that. So if we run this, let's also get, So here, when we compute this, here we'll just run this to get all of these basic parameters of GR. And the important thing is that not only do we need to find the Riemann tensor, but we also need to find the fully covariant form of it, because the covariant form is useful because it scales as you scale your coordinate system, which makes the determining of the properties that are coordinate invariant very easy. So we do this with the Ricci tensor. And so for example, let's see what this Ricci tensor looks like when we just plug this stuff. Again, there's much better ways to do this, but so if we actually decide to look at this, we get, we get nonsense. I mean, there's no way to figure out what this means. And as you can see in here, we have sines and sine of 2 theta squared times cosine of these random things. This makes no sense, and we can't do anything with it. Even Mathematica's simplify and trigger don't really make a dent in here. A similar thing for the Ricci scalar, which by the way is also the simplest of the 17 curvature invariants, because once we find these tensors, we'll combine them together to get these invariants. And the Ricci scalar is the simplest of these, and the simplest of the invariants still you can't really do much with it. So here we came upon our biggest challenge, which was actually harder than translating this into Mathematica, was simplification. Now, what we did is that we wanted to convert all of the trig functions in our tensors into just functions of one trig function. So to do this, we made a trig converter, which so we found since we couldn't figure out any way to do this built into Mathematica. Of course, we Googled it, and we saw a similar thing to this. It didn't quite do what we wanted to do, so we got it, we took it apart, and we improved on the code to create much better simplification. So just to get to the good stuff without going through how all this works. So for example, if we want to convert something basic like cosine of 2 theta to let's say cosine of theta. Or if we wanted to take something a bit more complicated than that, like, I don't know, sine of theta squared minus cosine, oh geez, this keyboard is weird, cosine of 3 theta, right? And we want to change that into cosine of theta. Then it can do that just like this. Now, we can't do this for everything, because for some functions, of course, are bivalued depending on where you are in which quadrant you're in. So if we just try to blindly apply to try to convert, let's say, sine of theta to cosine of theta, we'll get this bivalued function. Now, let's actually see how well this works with our code. So if you remember before, this Ricci thing, it was pages long. There's no way to make any sense out of it. Well, if we if we convert that whole long thing into just terms of cosine theta, then hopefully this doesn't take too long, then we'll be able to greatly simplify it. So let's see it. Remember that thing, I had to scroll forever. I didn't even get to the end of it. It was very long. Well, now it's just this. So immense simplification. And remember that the scalar thing, that was also extremely long. Well, when we convert everything in this into cosine of theta, we get 0. So that was really great. So the first invariant that we found is actually 0. And we were great to find this, but it's actually a known result that this is 0. So that was great for confirming what we did. Because we couldn't confirm all of the invariants because a lot of the invariants haven't been found yet. Now, to compute the first Weyl invariant, let's see, I'll run through this because I know you guys want to see the pretty pictures. So let's see, I don't think I actually have to run any of this. So, well, here is the first Weyl invariant here. And as you can see, again, pretty incomprehensible. Cosine of 2 theta, like where is all this cosine 2 theta to the 8th? Pretty funky, but when we run convert to it to make everything in terms of cosine theta, it's greatly simplified. Now, we had to do some massaging with this, so we just had to do some manual simplification, but here we have found the very first invariant, the very first curvature invariant, well actually, I guess the second one, well the very first non-zero curvature invariant for black holes. And this will allow us to have a much more accurate view of the interior of black holes than anything else. And this is actually what it looks like. And this is just showing the magnitude of the curvature. And there's some interesting things here. For example, in that earlier thing with the Borel-Lindquist, you saw there were these spheres, but they all had this positive curvature to it. And here you can see that in many places the curvature is negative. So that's an interesting result. So this is actually a first look into the interior of rotating, spinning, and charged black holes. Uh-oh. Well, I guess you can't have a Mathematica presentation without something going wrong. So, okay, so let's skip through the second Weyl invariant too. So, oh, okay. So, this is just to. So for the second Weyl invariant, we need to use the Levi-Civita tensor, and it's really complicated because it's not just a basic 2D tensor. So I think the best way to visualize it is to kind of take cross sections of it. But anyways, skipping through the results, this is what we got for the second Weyl invariant. And when we plot both of these together, let me make this bigger. Oh, we get this, and this is showing the relationship between these two different measures of curvature. And we can actually, something interesting is to show how this curvature changes as you change the angular momentum of the black hole, because we can see some pretty significant changes. So if we were to, actually I don't want to run this again because it's already here and it takes forever. So here you can actually see that as the curvature, or as you increase your angular momentum, the curvature stretches out, and it gets flattened, almost like a normal spinning object would expect. So, and again, there's some very important. What the? Oh. Well, all right. So the important thing is that these negative regions of curvature have some pretty important implications. So actually, in the literature that we were looking at, it was actually pretty controversial whether as R approaches 0, if you would get whether the curvature becomes negative. And a lot of things said that the curvature will stay positive always, even as you approach the singularity, but here we've shown that the curvature is actually, that the curvature does become negative as you approach as r gets small. Where were we? Now, I think the most beautiful way to express this is in spherical coordinates. Because when we take the first Weyl invariant and we put it into spherical polar coordinates, we get this is the best analog, the best accurate analog to that basic Boyer-Lindquist system. So that simple diagram from before that I just zoomed past, that's very inaccurate. I would say it's misleading depending on what you're trying to look at, but this is actually the most accurate representation of the interiors of black holes that we have. So let me make this a bit bigger. Let's hope it doesn't crash again. So yeah, here you go. And you can see, and it's very strange because again, it's positive in a lot of parts and then it's negative and it intersects with itself. And it's, what we've seen from this is that the interiors of black holes are much more complex and beautiful than we had ever previously imagined. So just to show this again with the changing angular momentum, you can see again how this flattens out, but I wish I could zoom in a bit more, but actually this is a list anyway, so I don't think I can change all of them. But anyways. Can you pixelize the animation slides? I don't think I can, no, because what I did is that since it's very computationally heavy, I made a bunch of, I just made a bunch of different values, so I can't rotate all of them. You can rotate this one though, this one looks nice. So I think this picture is the main picture. This is the main thing you should take out of it, in a sense, what the curvature inside of a black hole looks like. That we'll never be able to observe directly because of properties of the black hole.
It is an image of what exactly?
What?
It is an image of what?
It is an image of the curvature, of the magnitude of the curvature at different radii from the center of the black hole. So actually, the larger value, as it goes out, this is actually r getting smaller. So you can see that the curvature is very large as you approach the singularity, and then the curvature gets smaller the farther out you go. But as you go through different regions of the black hole, the curvature does a lot of different things. Yes, yes. This is the Weyl invariant, and just some other interesting things from this is are these regions of negative curvature, and I actually personally don't know a lot about this, but the people in my research group, they actually determined some very interesting relationships that come from this negative curvature. For example, so some implications is that the jets that you can see coming from some active galactic nuclei are related to this negative curvature that results from deep inside the event horizon of the black hole. From inside the event horizon, this negative curvature can result in these jets. And also these really, really beautiful Fermi bubbles. This is also thought to emanate, or is thought to be related to this negative curvature. And so just some conclusions. So the curvature inside actual black holes, not these approximations, can have both negative and positive values, certainly not constant, and very complex. And the interiors are much more complex and beautiful than we ever imagined. And let's see, what else is? Yeah, just that the biggest thing about what we discover is that we don't actually know exactly what all the implications of this are. So with these, but the first step into discovering what these mean is to find them. And that's what we've done here for all 17 curvature invariance. So thank you. Yeah.
So I assume this was a stable black hole, non-merging. So 100 milliseconds after one of the mergers, what is it possible to understand what that looks like?
Well, we haven't done that, and what we calculate here, yeah, were for stable black holes that didn't just go through a merger, but I couldn't see a reason that we couldn't. I mean, if we can map out mathematically the interiors of two black holes, we can simulate, of course, what their interiors would look like, and I can only imagine what that must look like.
Is there a relationship between what I'm interpreting as the space-time curvature and the mass density inside the black hole?
Yes. Simple answer. Yeah, it's no.
This is the trace of the Weyl tensor, which means so it's related to sort of energy flow, but not energy density.
Okay. That's it. So the
Right.
Yeah.
Energy density comes from
Yeah. Okay. Yes.
frequency scale.
Yeah. All right.
Can you get to energy density from
From Weyl.
All right. So yeah. Thank you. I gotta get out of here now. I'm holding everybody else up.